Every time you use a compass, you're experiencing one of the Earth's most powerful forces, its magnetic field. When most people think about this field, they picture a giant, invisible, donut-shaped bubble that surrounds the planet. And they're mostly right. This is the core magnetic field, and it's the primary magnetic shield of the Earth. The core field is generated deep beneath our feet, not by a simple bar magnet, but by something far more dramatic: the dynamo process. Deep in the outer core, liquid iron and nickel are churning at incredibly high temperatures. This movement converts kinetic energy into magnetic energy, creating that vast, powerful dipolar field that protects us from solar radiation and guides our traditional compasses. Because the core field is generated by liquid, moving metal, it is constantly changing. Over very long periods, hundreds of thousands of years, the entire field can actually flip polarity, meaning north becomes south. The core field is powerful, but it's not a fixed reference. It's too changeable to be a precise anchor point for modern navigation. But the core field isn't the only source of magnetism. There is one sitting right beneath us: the crustal magnetic field. The crustal field is entirely different. It's a fossil record, a history log written in stone. When igneous rocks cool down, they pass a critical point called the Curie temperature. Below this temperature, tiny magnetic domains within the rock minerals permanently lock in the direction and strength of the current magnetic field. When the rock is finished cooling, it becomes its own tiny permanent magnet, reflecting the core field as it existed at that moment in time and place. Because this process has happened countless times over billions of years, the Earth's crust is covered in a fixed pattern of stronger and weaker magnetic regions. This pattern is often called the magnetic anomaly or the magnetic fingerprint, and it is extremely stable over human timescales. So how can this be applied to navigation? When measuring the magnetic field close to the ground, you're picking up both the core field and the crustal field. To isolate the useful crustal signal, highly sensitive instruments called magnetometers are used, often mounted on aircraft. Analysts then mathematically subtract out the smooth, predictable core field using sophisticated models. What remains is the unique, localized crustal fingerprint. And because this fingerprint is stable, it can be mapped out beforehand. An advanced navigation system can then read this magnetic fingerprint in real time and compare it to the map to determine their precise position. This technique creates an unjammable navigation alternative to GPS. The crustal field gives us a stable, non-drifting magnetic map, ready to guide the next generation of resilient navigation.